Okay, so we've discussed the predictive distribution for the Bayesian linear regression problem. Next, I want to show how this predictive distribution has more uses than simply making predictions for new data. And this is through something called active learning. So we can naturally think of Bayesian learning as a sequential process where we have a prior belief of a model variable. We get data, and through that data, we then calculate our posterior belief of the model variable. And then that posterior becomes the prior for the next data. So we use the posterior in the predictive distribution to help us give us a prior distribution of what we think the model variable will be. Okay, so we've discussed Bayes' rule for the linear regression problem and predicting new data. Let's now look at something that combines both of these two techniques, something called active learning. So active learning is a general technique for learning a model efficiently, and we're going to discuss it in the context of Bayesian linear regression. So Bayesian modeling can be thought of as a sequential process where we see a sequence of data, and given everything that we know up until a certain time point, we calculate our posterior belief of the model variables. We use that to then make a prediction for a next observation. And after then seeing the next observation, we update our posterior belief. And so the idea of active learning is to do this efficiently. So imagine that we have options, we have choices in how we measure the data or which data we observe next. Is there a sequence that we can follow to somehow observe data that is going to give us a lot of information about towards the end goal of calculating our posterior on the model variables? So for Bayesian linear regression, what we have is something like this. We have that if we let y and x be the old data and y naught and x naught be some new data, by Bayes' rule, we can calculate the full posterior given all of the data as being proportional to the likelihood of the new data, y naught, given the model variable w and given the x naught that we observe, times the posterior of the model given all of the old data. And so we see that Bayes' rule can be used in multiple ways. We don't necessarily have to make this likelihood over all of the data and this prior be the original prior. We could also make the likelihood over the last observation, and the prior in that context becomes the posterior given all the previous observations. So for the linear regression model, we have a posterior that looks like this, where we can see how we make a very simple modification to the posterior given the new data that we observe. So the posterior covariance can be written in this way, where I've intentionally separated out the next observation, and the posterior mean can be written this way, where again I'm pulling out and separately writing the new observations that we have, whereas this is, for example, a sufficient statistic that we just keep. We keep the cumulative sum of outer products and the cumulative sum of these vector scalar products, and we treat this as a single vector that we then update in this way, and this as a single matrix that we update in this way. Okay, so let's now look at how we can use this sequential Bayesian learning to learn the model posterior more efficiently. And I should say that this is only really useful in the context where we really do have a sequence of observations that we get to choose from. So if the sequential aspect of learning does apply to the problem, then this will be useful. But if we have all of the data already, then this isn't necessarily something that we'll want to do. Okay, so we've seen how learning W, so learning a posterior of W and then making predictions for the next response is really a two-step procedure. So what we do is we first form the predictive distribution of the response of the new, that corresponds to the new covariate vector that we measure, x0, given all of the old data. And then using that measured response, we update the posterior, as I've shown in the previous slide, by a rank 1 update, or adding a vector to a sufficient statistic. So now let's think of how we can efficiently learn the posterior when we get to choose the sequence of measurements or of observations that we have. So for example, imagine that we have a data set of covariates x1 through xn. So we've gone into a field and we've measured many different locations in the ground, and so we have some sort of perhaps a frequency response for n different locations, and now we want to pick which sites are we going to dig so that we can measure the actual response, whatever it may be, in order to learn our posterior more efficiently. And you can see why this would be a useful thing to do. For example, if measuring a yi that corresponds to an xi somehow costs money, maybe you have to destroy something, maybe you have to dig a big hole in the ground, so it's somehow expensive to observe this yi, we want a way of sequentially picking these responses so that we're going to get a lot of information about our posterior of w. So first, let's intuitively think of an active learning strategy that we could do to perform this task. So this is just a heuristic, and then I'll make it more formal in the next slide. So imagine that we already have a measured data set, yx, and therefore we've computed the posterior distribution of w given yx. We can then construct the predictive distribution for all remaining x0 in our data set. So these are all the x0 in the data set for which we don't have the corresponding response. And so we've seen how that predictive distribution can be written this way. The distribution of the response associated with an x0 given a y and given an x can be written as a Gaussian where the mean is the dot product between x0 and the posterior mu. That's the posterior distribution here. And the variance of our prediction is written as the noise variance plus this quadratic product of between x0 and our posterior covariance, where that covariance is from the Gaussian posterior of w. So for every x0, we can calculate these two values, and the value of sigma naught squared, in a way, it gives us a measurement of how confident we are in our prediction. So for different x0, we're going to have different measurements of how confident we are in our prediction of mu naught, in a sense. So this suggests the following procedure. First, form the predictive distribution on all data in our set that do not have the corresponding response. Then pick the data point x0 for which our uncertainty is the greatest, and measure the corresponding response. So then actually decide to go into the field and dig a hole in the ground or perform a lab experiment that might cost some money. Then update the posterior distribution of w using the new augmented data set, where y is the old data augmented by the new response, and x is the old data augmented by the new covariate vector. And then return to 1 and continue this process, where at every step we're choosing to measure the response that corresponds to a covariate vector that we're the least certain about in our prediction. So this intuitively makes sense. It seems reasonable. But now the question is, what is it that we're trying to optimize when we do this?